Hello and welcome to the Manfred Olson Planetarium's virtual program, Bizarre Black Holes. This is in collaboration with the Center for Gravitation, Cosmology, and Astrophysics at the University of Wisconsin-Milwaukee. My name is Jolien Creighton. I'm the director of the planetarium, and it is my very great pleasure to introduce a black hole expert, a senior member of the LIGO Virgo scientific the LIGO scientific collaboration, and to introduce my my own husband, Jolien Creighton, who will talk to us today about black holes. And he will, I guess, begin with telling us why he has been so interested in black holes for his career. Thank you. There will be an opportunity to ask questions in the Q&A. So there's a Q&A as opposed to the chat at the bottom of your screen. And we will answer questions at the end of the program. So you can feel free to put them in the Q&A as they come to you. And with that, I'll let Jolien take it away. Thank you for joining us.
Okay, thanks. So today I get to talk about black holes, which I've been interested in for basically my entire life. I might throw in a few neutron stars, which are kind of interesting too, but mostly going to focus on black holes because they are very interesting and unique objects. They're holes in space where anything can fall in, but absolutely nothing can come out. And to paraphrase a famous astrophysicist named Chandrasekhar, black holes are the most perfect objects in the universe. The only elements in their construction are our concepts of space and time. Now, black holes have also been in the public interest recently because 2 out of the past 4 Nobel Prizes in physics were awarded to researchers doing research in black holes. So what we're going to do is, first of all, I'm going to talk a little bit about what a black hole is and try and give you some insight into these rather difficult to explain things because they're so counterintuitive. Then I'm going to spend some time talking about how do we know that they're there and how do we study things that produce no light whatsoever? How do we see them? At the very end, I'll talk a little bit about the future of looking for black holes, the future of astrophysics, at least in terms of studying black holes and neutron stars. So there is an original concept of a dark star, which is not exactly a black hole, but it's a nice analogy of a black hole. So we'll spend a few minutes describing what a dark star is. This first came about by John Mitchell in 1783, and at that time the laws of physics were Newton's laws of physics, and the laws of gravity were Newton's laws of gravity. So this is a very Newtonian notion of what something like a black hole is. And what it is it's a star that's so dense that the light emitted by the star doesn't get away from the star. It gets pulled back down and bent around and falls back down onto the star. And so we would never see such things. They could be out there in the universe and we would never see a dark star. The light would never get to us. And to go into a little bit more detail, we need to talk about something called escape velocity. So if you imagine standing next to the Eiffel Tower, and suppose that you were to throw a baseball directly upwards, say about as fast as a human can throw a baseball, about 100 miles per hour, then of course the baseball would go up and fall back down. So it would only get about a third of the way up the Eiffel Tower at that speed. Now you can imagine throwing the baseball twice as fast, 200 miles per hour. And now it would get nearly to the top of the Eiffel Tower before falling back down. But it still falls back down. But if I were to throw that baseball upwards at, say, 25,000 miles per hour, or Mach 33, then it would fly up and we could keep waiting, but it's never going to come down. So that was fast enough that it actually escapes the Earth's gravity, and that baseball will keep flying off into space and it'll never be turned around and fall back down. Well, that's what the idea of a dark star is. If we take the sun and look at the surface of the sun, then there's all this light being radiated away from the surface of the sun, and at 670 million miles per hour, that light certainly has escape velocity from the surface of the sun, and it flies away from the sun. We see it on the Earth. We see other stars in our galaxy. The light from those stars are escaping their surface. But what Mitchell realized is that if you take the sun, all of its mass, and compacted it into something much smaller, say about 10 miles in circumference, so 10 miles around it, then at that point, the gravity at the surface of the sun would be so great that even light shone away from the surface wouldn't have the escape velocity. So it would get turned around and fall back down onto the surface of the star. So at that point in time, you wouldn't be able to see the sun. It would be a dark star. Now, this idea is firmly rooted in Newtonian mechanics, and there's several things that are different about this dark star and what we'll see as a black hole. For one thing, if the sun turned into a dark star in the center of our solar system, well, then we would lose all the light from the sun, but we could still imagine studying it. We could fly our spaceship in, sort of hover near the surface, look at the light from the star. There's nothing saying in Newtonian mechanics that we can't travel faster than the speed of light. So we can take a good look and then fly back home. And that would be all very fine. But there's a problem with this idea of a dark star when you look at it in terms of general relativity. And the problem basically is that as this light leaves the star and then falls back down, there's that moment just when it's just stopping going up and starting to go down, when it's momentarily at rest. But in relativity, that can't happen. Light can never be at rest. Light always travels at exactly the speed of light. So at that moment, this dark star would be violating relativity. So that's not quite what a black hole is. So let's talk instead about what a black hole is in general relativity, in Einstein's theory of gravity. And so we're going to discuss the anatomy of a black hole here. And what's shown here is a black hole. It's a simulation of a black hole surrounded by a swirling disk of matter. And that disk of matter is basically there so that we can see some of the features that we're going to talk about. So the defining feature of a black hole is what's called the event horizon. So that's shown in that dotted circle in the middle. The event horizon is this region, this surface. There's nothing there, it's completely vacuum, but it's a surface where if you cross it going inwards, then you can never cross it going outwards. All right, and this is because of a trick of how space and time warp. What happens is, when you're outside of the event horizon, then there's the concept of moving towards the center and away from the center. We think of those as spatial concepts, quite distinct from, say, moving forward in time or backwards in time. The future and the past, we can imagine going towards the center as we move forward in time into the future, or we can imagine going away from the center. Those two, the space and time are quite separate when we're far away from the event horizon. But as we move from just outside of the event horizon to just inside of the event horizon, then the space and time sort of flip over in a sense. And now, once I'm inside the event horizon, moving towards the center is actually the same as moving into the future. And moving away from the center is the same as moving into the past. So future and past now are the same as towards the center and away from the center. Okay, so that means that if I'm inside the event horizon, then everything outside of the event horizon is not in my future anymore. I can never get out of the event horizon. That's just not, my future always is moving towards the center. And if nothing outside of the event horizon is in my future, then for anyone outside the event horizon, I'm no longer in their past. So this event horizon is a causal boundary that separates one portion of the universe from another portion of the universe, and they cannot have any causal relation at that point. Okay, so at the very center of a black hole, there is a singularity. And the singularity is a point of infinite density where all the mass of this black hole is concentrated. It is also a point of infinite curvature of space-time. And this is a place where the theory of general relativity basically breaks down. It can no longer describe what's going on at that point. Because towards the center is forwards in time, we think of this singularity as not really so much a point in space, but a moment in time. And once I'm inside the event horizon, that moment of time will come all too quickly. As I approach it, it'll be ripped apart by the gravitational forces. Okay, so we don't we don't really understand singularities. We certainly don't want to encounter one. But the fortunate thing is that it's not in our section of the universe that can never affect us because it's covered by this event horizon. So I described at the beginning this swirling disk of matter. Many black holes, but not all black holes, have things called accretion disks, which is the swirling mass of gas surrounding the black hole. And they're very handy for us because the accretion disks give us a way of actually seeing where the black hole is, because the black hole obviously is not going to be producing any light. Now, there's some interesting optical effects going on with this accretion disk, which you probably have been noticing all this time, that you can see the disk moving in front of the black hole here, and that all looks sort of normal. But then there's this, what's this going on over there and under there? Well, it turns out that the gravitational pull of the black hole is strong enough that the light from the far side of the accretion disk is bent over the top of the hole and comes towards us from this vantage point. And so what we're actually seeing over here is the top side of the accretion disk on the far side of the black hole. And down here, we see the bottom side of the accretion disk on the far side of the black hole. And that's because the light is being bent around the hole by its gravity. Okay, another interesting optical feature you see here is this ring going around the event horizon. This is not at the event horizon. This is slightly outside the event horizon. And what's going on here is that if you have light and it's not traveling away from the black hole, but sort of traveling laterally, then the gravitational pull is strong enough to bend this light so that it goes in a circle, and it keeps going around and around and around and around and around the black hole, forming this thing called a light ring. So that's what that very thin ring, sort of between the inner edge of the accretion disk and the event horizon is. Now, there are two types of black holes that we know of in our universe. There are stellar mass black holes and supermassive black holes. Stellar mass black holes are around tens of times the mass of the sun, so sort of around similar masses as stars, or massive stars anyway. Supermassive black holes, by contrast, are millions or billions of times the mass of the sun. And we see stellar mass black holes, primarily we see them in our galaxy in X-rays that are emitted from accretion disks like this in X-ray binaries. Supermassive black holes, however, we find in the centers of galaxies. So practically every galaxy out there has a supermassive black hole lurking in its center. And we can see those from jets of radiation that are beamed out of the centers of some galaxies. We know where, or we're pretty sure we know where the stellar mass black holes come from. They're an endpoint of the evolution of a star that is reasonably massive, say about 10 times the sun's mass. So the basic idea of a star is, what a star really is it's this ball of hydrogen that is collapsing under its own weight. It's causing it to collapse. And at some point in time, the center becomes hot enough that nuclear fusion starts occurring, which produces a lot of energy in the center of the star, and that energy provides the pressure that supports the star against the collapse. So the fusion is converting hydrogen into heavier elements. And that stops the collapse, and we have a stable star that will last millions of years. But eventually what happens is that the hydrogen in the center of that star starts to get used up. It starts to get converted into higher, more massive elements. When that first starts happening, the star evolves into what's called a red giant phase, where the star grows very large and red. And that's sort of signaling that the star is almost done using up its fuel. And when that fuel is completely used up, then the core of the star no longer can support itself. There's nothing no fuel left. So that means that there's nothing to stop it from freely collapsing. So it very quickly collapses, implodes upon itself. And the release of the tremendous amount of gravitational energy that causes produces a blast of energy that blows up the rest of the star in what's called a supernova. What's left of that core of the star that collapsed is a black hole if that core was massive enough to undergo complete gravitational collapse. If it wasn't, then we might be left with something that's not quite as small as a black hole, called a neutron star. So this is a star made mostly out of neutrons. It's roughly like a very massive atom, but by very massive, I mean about the mass of the sun. By contrast, it's not so clear where the supermassive black holes come from. This is actually one of the mysteries that is a lingering problem in astrophysics, is how do we know where the stellar mass black holes come from, but how do we get a black hole that's millions or billions of times the mass of the sun? So this is an artist's impression of a supermassive black hole, which is from the movie Interstellar, which came out a few years ago. And I'm highlighting this movie because the executive producer of this one of the executive producers of this movie was Kip Thorne, who was my postdoctoral advisor. And he was consulting with the movie to make sure that they got the black hole physics approximately correct. Okay, so now let's discuss a little bit about the theory of black holes. So only a few months after Einstein published his equations of general relativity, Carl Schwarzschild found a solution to these equations, which we now know is a black hole solution. It's called the Schwarzschild solution. And at the time, the black hole nature of this solution was not fully understood. The event horizon wasn't fully recognized to be an event horizon, and the interior was completely missing from the solution. But it was studied sort of as a mathematical curiosity for the next few decades. But people didn't really consider this to be more than a mathematical curiosity, some sort of particular solution of the theory that had some bizarre properties. There are lots of particular solutions of the theory of general relativity that have bizarre properties, time-like curves, time machines, all sorts of things. But we don't really expect that those peculiar solutions actually exist in nature. So this viewpoint started changing in the 60s and 70s, and largely in part by research that was done by Roger Penrose and Stephen Hawking and many other theorists at those times, who started to realize that the gravitational collapse, such as at the end of the life of the star, under very generic, extreme but generic conditions, must inevitably lead to produce one of these singularities. That is, the collapse would continue indefinitely, and that there would be no, at a certain point in the collapse, there is no way that the matter could possibly not collapse to form a singularity. So Roger Penrose took a new view of of understanding special relativity. He was interested in the edges of space-time, so the beginnings and the ends and the infinities of space-time, and that's sort of a new approach to understanding space-time that Roger Penrose brought about, and that gave mathematical tools to start looking at these very generic theorems about singularities. And he was able to show, as I said, the inevitability of complete gravitational collapse leading to these singularities. He also studied the event horizon and was able to describe that with prove various theorems about the event horizon. And he put forward a conjecture, which we certainly hope is true, but it's a conjecture that all of these singularities that are produced by complete gravitational collapse will be shrouded by an event horizon. So none of those singularities will, where space and time become infinite and who knows what could happen, those are all safely protected from our universe by event horizons. So they're safely locked in black holes. And just this past year, Roger Penrose won the Nobel Prize for this research on black holes. Okay, so now we're going to move on and look at how one might start to try and study these objects that are all over our universe, but don't emit any light. So these two astronomers shared the Nobel Prize with Roger Penrose, Andrea Ghez and Reinhard Genzel, and they studied a supermassive black hole in the center of our galaxy by looking for its gravitational signature. So the black holes do not produce light. This black hole doesn't produce light, but it does have a gravitational field. It does produce gravity. And so over the course of decades, they monitored the motion of stars right at the very center of our galaxy to find that those stars were orbiting around something with a huge amount of mass, but there was no way to see it. So what's shown here is the course of decades following looking at a cluster of stars right at the center of our galaxy. That 5-pointed star is just drawn in there. That's the location of where the black hole is. And over these decades, we see all the other stars, the real stars, the ones we can see, moving in elliptical motion around this point, which must be a source of gravity, but doesn't produce any light. So in particular, this star S02 came very, very, very close to this black hole. It came closer to the black hole than we are now from the Voyager spacecraft. And at that moment that star was sweeping by that black hole at its closest approach, that star was moving at about 3% of the speed of light. So very close to this black hole. And by mapping these orbits, they were able to show that the black hole in the center of our galaxy is about 4 million times the mass of the sun. And this is definitive evidence that there must be a black hole in the center of our galaxy. There's no other way that you could cram that much matter into a space that small, and certainly not without being able to see it. Okay, if we want to actually see the black hole, something like that accretion disk with the swirling matter and the light being bent over the top and the bottom and all that stuff that I showed in the anatomy, we need to be able to see something very, very small that's very, very far away. So we need a telescope with extremely high resolution. And so the Event Horizon Telescope is a telescope that was operated just to do that, to study the black hole in the core of a galaxy. And the way they did that is they built a telescope that's aperture, the size of the aperture of the telescope is in fact the size of the Earth. And to do that, what they did is they used various telescopes located in various different parts of the Earth and shared the data between those telescopes and synthesized a single telescope with that huge aperture. And in so doing, they were able to get a telescope that was big enough to have the resolution that we could actually peer down into the center of a nearby galaxy. So this is the galaxy M87. It's a giant elliptical galaxy, relatively nearby. And they looked at this supermassive black hole at the center of that galaxy. Now this one has billions of times the mass of the sun. And you can sort of see in this diagram this jet of radiation coming from the center. That's a jet of radiation produced by the black hole and its interaction with the accretion disk. And that jet is basically the size of a galaxy. It actually extends out past the galaxy in some wavelengths. So what I'm going to show is a video that zooms into to the center of that galaxy and finally resolves that accretion disk. Okay, so here you see sort of a slightly blurry version of what we were looking at with the anatomy of the black hole. We see the shadow of the black hole in the center. We see the accretion disk itself in front, and we see the back of the accretion disk sort of bent over the top of the black hole over here. What's also interesting about this image is that you can sort of see these streaks of lines, and that's because this image was produced by looking at the polarized light from the black hole. So like with polarized glasses, you're only looking at light waves with the fields going one way instead of the other way. And what this is indicative of is that there are magnetic fields in this accretion disk. And the magnetic fields thread through the accretion disk and the black hole itself. And that produces the mechanism by which you can power the engine that drives that beam of radiation out of the galaxy. So you're able to actually make measurements of the magnetic field in that accretion disk as well as seeing it. Okay, there are other ways that we can look at black holes, if you use the term look rather loosely. So black holes don't produce light, but they do produce gravity. And pairs of black holes produce what are called gravitational waves as they orbit each other. So gravitational waves are ripples in space-time. And now space-time is the geometry. So by the ripples of space-time, we mean distortions of the geometry of space-time. All right, space-time is the thing that determines what the distances between objects are, what is the future and what is the past, and all of these measures of geometry. And these ripples in space-time are distortions in that. They're gravitational distortions. And they can radiate away from binary systems, such as black holes or neutron stars, and travel through the universe where they arrive at Earth. Now, the effect of a ripple in space-time, well, the space-time, I said, is describes geometry. And so a ripple of space-time is a ripple in the geometry of things, where the gravitational wave travels. So in particular, as a gravitational wave passes through, it's going to change the geometry or the proportions of objects. So it might, as a gravitational wave comes through, it might change circles into ellipses, squares into rectangles, or that kind of, or have that effect on geometry. So in particular, if a gravitational wave were passing through me, as it passes through, I might grow taller and narrower, or I might grow shorter and wider, depending on which way the gravitational wave is distorting me. Now, gravitational waves are passing through me all the time. They're passing through you too. They're passing through everything all the time. And you might have noticed that this doesn't seem to happen very much. And the reason is because the effect is very minuscule. So if I were to try and measure the distance between us and a nearby star, like say Alpha Centauri, then a gravitational wave passing by will change that distance between us and Alpha Centauri, but a typical gravitational wave will only change it by something less than the width of a hair. Okay, so this is entirely and completely undetectable, or at least almost entirely and completely undetectable. So for the past couple of decades, there's been a worldwide attempt to try and detect gravitational waves. Several gravitational wave detectors have been constructed, including the LIGO detectors. That stands for Laser Interferometer Gravitational Wave Observatory. And there are two of these in the United States, one in Washington and one in Louisiana. And there are other detectors operating in the world. There's one called Virgo in Italy. There's one called GEO in Germany. And there's one called Kagra in Japan. So there's a worldwide network of these gravitational wave detectors. Now, if you look at them, they all look kind of the same. They've got some sort of building in the middle and two arms radiating away from it. And the basic idea of how these are trying to detect gravitational waves is to try and measure changes in the lengths of these arms. Now, these arms don't go out all the way to Alpha Centauri, of course, so the amount of change in the length of the arm is even going to be smaller than the hair's width. It's going to be much smaller than the size of a nucleus of an atom, in fact. But the basic idea for how you want to detect these is you fire two light beams out from the center. They get reflected off the end stations and return to the center. And if those arms are exactly the same length and you fired those two beams of light at exactly the same time, then they should come back at exactly the same time. But if a gravitational wave comes and stretches one arm a little bit and squeezes the other a little bit, those two beams of light might come back at slightly different times. And that would be the signature of a gravitational wave. All right, so to explain that in a little bit more detail, what's actually done is a laser interferometer. So what we see here is a laser, and the laser beam leaves the laser and hits this mirror here, which is called a beam splitter. So what it does is it lets half the light pass through and the other half gets reflected. So now we have two beams of light. One goes up one arm, the other goes up the other arm. At the ends of the arms, there are mirrors, which reflects it back towards the beam splitter. Now, in this interferometer, if these two paths, if these lengths of the two arms are exactly the same, then when the light recombines at this beam splitter, it will all travel back towards the laser and none of it will travel in this other direction. But if one of the arms is slightly longer and the other is slightly shorter, then we get this, what we call destructive interference this way, will not be perfect destructive interference, and a little bit of light will come out here and be detected over here on this light detector. So we can see this if we now represent these light waves as waves with crests and troughs. So the two sets of light beams return at the beam splitter, and then over here we see that all the crests of one ray are lining up with the troughs of the other, and we get destructive interference. But when the lengths of the arms change, the crests might line up with the crests and the troughs with the troughs, and then that means that the light is actually coming out of that in that direction and will be visible on that light detector. So we look for very, very small changes in the lengths of the arms through this method called laser interferometry. And a little over 5 years ago, LIGO made the first detection of gravitational waves on September 14th, 2015, with this event called GW150914. And these gravitational waves were produced by a pair of black holes in a distant galaxy that were orbiting each other and merged and produced the gravitational waves that we saw. So here we see a computer simulation of the system of black holes. And on the bottom in colors, we see a representation of the curvature of space-time produced by these two objects. And as these two black holes merge, there is a burst of curvature that radiated outwards into the universe, eventually arriving at us, leaving behind a single, so you see the radiation traveling away from the system, leaving behind a single perfect black hole. For this discovery and for the construction and conception of LIGO, the Nobel Prize in 2017 went to Barry Barish, Kip Thorne, and Rainier Weiss. Since then, LIGO has detected many such binary mergers of black holes and neutron stars. So in this diagram, I'm showing all of the LIGO detections as well as a few other known black holes and neutron stars. So in the vertical axis, we have the masses of our various objects. And up in this top part, we have in blue the LIGO Virgo black holes detected in gravitational waves, as well as black holes in purple that are detected in X-ray binaries in our galaxy. And if you look at these, the LIGO Virgo ones come in these funny triple diagrams. What this means is that we had two initial black holes, one slightly less than 20 solar masses, so the vertical axis is mass, one a bit more than 20 solar masses, and the two came together and formed a black hole that was more than 40 times the mass of the sun. Down here, these lighter objects are neutron stars. They're about the mass between 1 and 2 times the mass of the sun. In yellow are neutron stars in the galaxy with known mass, and these are observed in radio waves or X-rays. And there are also two binary neutron stars that have been observed by LIGO and Virgo in gravitational waves. So this event here is the one I described just before, GW150914, the first detection of gravitational waves. But I also want to talk a little bit about the very first binary neutron star ever observed, which was in 2017, in August 17th. Now, unlike binary black holes, neutron stars are made out of matter, mostly neutrons. So when they merge, they produce all sorts of interesting phenomena, not just one empty black hole. So what we saw there was the merger of two neutron stars, visualization of the merger of two neutron stars. And when they smashed into each other, there was first a burst of gamma rays, and then this explosion of all this ejecta of this very neutron-rich material in this big puffy cloud that is highly radioactive and glows very brightly. So when LIGO detected these gravitational waves, within just a couple seconds, that burst of gamma rays was detected by gamma ray telescopes on satellites. And then based on the information that LIGO provided about where this was on the sky, a huge number of telescopes all of a sudden were scrambling, trying to find the glow from this massive amount of material that was blown out of this explosion. And within a day, they were successful, and they managed to find the glowing remnant of this collision with somewhere in a nearby galaxy, and then watch it over a few days as it faded and then eventually disappeared. What's interesting about this observation is it allowed astronomers to answer one of the mysteries in astronomy that has been around for a while, which is where do heavy elements in the universe come from? So we know that many elements heavier than hydrogen and helium come from supernovae explosions, what I talked about at the end of a massive star's life when it blows up and it scatters debris, including heavy elements, into the galaxy. But that can only explain the abundances that we see for some elements, mostly these ones over here that you see in mostly green. Those are elements that are created by exploding massive stars, so in supernovae. But these other elements, these heavier elements, the lower ones on the periodic table, we can't explain those abundances with supernovae. And so it was a bit of a mystery, where were all of these elements coming from? Well, by analyzing this ejecta of what we know was a binary neutron star merger, we could see that this was a place where a lot of these heavy elements were being forged. So we now know that a lot of these heavy elements now in orange, the things that are primarily in orange, are actually formed in binary neutron star mergers. So merging neutron stars are responsible for all of these elements in the universe. So in particular, this element here, gold, is almost entirely made in merging neutron stars. The system that we saw in 2017, that merging neutron star, produced approximately a planet's mass worth of gold in the ejecta. And then that was scattered about in its galaxy and will presumably coalesce in stars and planets in that galaxy. So all the gold that we have here on Earth, or anyway, most of it, we now know came from some ancient binary neutron star merger billions of years ago in our galaxy. Okay, so LIGO can see black holes and neutron stars, but it really only sees the stellar mass black holes, the ones that have masses of tens or maybe even 100 times the mass of the sun. It can't really tell us much about supermassive black holes. And remember, I said that we don't really know where supermassive black holes come from. That's another remaining mystery. But because supermassive black holes orbit each other so slowly, LIGO can only see things that are orbiting around about hundreds or thousands of times a second. So it basically can't see supermassive black holes. So if we want to search for supermassive black holes using gravitational waves, we need to use a different technique. So this is another project which scientists at UWM are involved in, called NANOGrav, which is a method of trying to measure gravitational waves, this time from supermassive black holes, using what's known as pulsar timing. So this is the North American Nanohertz Observatory for gravitational waves. So the basic way that that we try and measure gravitational waves using pulsar timing is, well, first of all, what is a pulsar? A pulsar is a special kind of neutron star. There are many known in our galaxy, and they are rotating neutron stars with strong magnetic fields, and those magnetic fields produce beams of radiation leaving the surface of the neutron star. So as the neutron star rotates about, those beams of radiation circle about. And if we're lucky enough, then some of these beams of radiation will be pointed at the Earth. And every time it sweeps around, we will see a flash of the radiation from these beams, sort of like a lighthouse sweeping around. We will see flashes of light every time the lighthouse light is pointed at us. So a gravitational wave is a distortion not only of the proportions of geometry of space, but it also distorts time. So these neutron stars, which are spinning around very regularly, they are extremely precise clocks sitting out in space. As a gravitational wave passes by them, their time will change due to the passage of the gravitational wave, and we will see them slowing down or speeding up in their rotation. Went the wrong way. So here we see the neutron star spinning around, flashing its beam of light at us. As the wave passes by, the flashes will become slower and slower. And then as it goes by, it resumes its regular rate. So that's how NANOGrav is looking for gravitational waves. And recently, they've just had some hints of that they might have detected gravitational waves from supermassive black hole binaries. So stay tuned to hear more about that. Okay, so I'd like to just spend a couple minutes talking about some of the things that are coming up in the future. So first thing I want to talk about is the future of multi-messenger astronomy, by which I mean we're doing astronomy not only with light, but also with, say, gravitational waves, looking for things like the binary neutron star merger. So LIGO is going to continue operating and hopefully with improved sensitivity, give us many, many more detections. And here we see the Vera Rubin Observatory, which is being constructed, which will be able to very quickly be able to follow up and find those afterglows from LIGO events. And here's an artist's conception or rendering of the completed Vera Rubin Observatory. It actually probably looks a lot more like this than it does like this now. This is a bit of an old picture. It's a year old. And hopefully Vera Rubin will start observing within the next year. In the more distant future, there are designs to build far more sensitive gravitational wave detectors. So one concept is the Einstein telescope, which would be an underground detector, but with arms that are 10 times longer than the arms in the current detectors and much more sensitive. So these next generation of gravitational wave detectors will be able to see not just handfuls of binary black holes or binary neutron stars, but we'll be able to see every single binary black hole or binary neutron star merger in the entire universe. So approximately 1 every 10 seconds. And then to further study the origin of supermassive black holes, there is a planned NASA and European Space Agency mission to build a laser interferometer in space. So this is the laser interferometer space antenna, where now we have a constellation of satellites orbiting around the sun, trailing the Earth, with incredibly long, 2 million mile long arms. And this observatory will be able to detect supermassive black holes throughout the universe, and hopefully we'll see the black holes, the intermediate mass black holes, and tell us how we get from stellar mass black holes to supermassive black holes. And so with that, I'm going to stop and maybe answer some questions.
Okay. I'm gonna give you some questions here, and if people have them, they can put them in the Q&A part. So Sean asks, what did you think of the movie Interstellar, and how accurate would you, I mean, you said that the person you worked with, in fact, was giving them advice about the accuracy, but what thoughts did you have about the movie?
It was a trade-off between artism and reality. More than most science fiction movies, I think it was attempting to be more accurate, and in particular, some of the physics about the black holes was actually mathematically correct, although the black hole that was under consideration was rather implausibly, was spinning implausibly fast. So the calculations were right, the physics was right, but it was probably an unrealistic supermassive black hole. It was spinning too fast.
Okay. This is from an anonymous attendee. Why is density and gravitational pull connected in the first place?
Okay, so the gravitational pull is produced by mass. Okay, and so the density of the object is the amount of mass that you fit in a given amount of volume. All right, so if I've got a certain amount of volume and I put more mass in it, then it becomes more dense. All right, the gravitational field also depends on how far away I am from the center of the object. So if I want a very strong gravitational field, I want to be close to the center, but with lots of matter. So that means I got to put a lot of matter into a small space. And that means that I have to have a very dense object.
Who is Vera Rubin? How many women have such places named for them?
Oh, I think you're the expert for answering this.
Well, let me say that Vera Rubin is one of my heroes. She was the first person who provided data that there is dark matter, what we describe as dark matter in galaxies. That is, that stars toward the edges of galaxies are moving much too fast for the gravitational field that we see, the mass that's visible to us. So we're still searching for dark matter, and that is one of the scientific goals that the Vera Rubin telescope has. And how many women have such places named for them? Not many. So it's time to change that. All right, so let's see. What is your opinion, thoughts on time travel?
Time travel, it'd be great. So time travel is, there are solutions to Einstein's general relativity that involve what are called closed time-like curves, so basically time travel. So it is not ruled out by the theory, but the question is, does anything like that actually exist in our universe? Does anything exist in our universe? So the answer is probably not, but that's kind of the same answer that people said about black holes for many decades. So perhaps.
Perhaps is perhaps a more prudent response. All right. In the plot showing all the black hole mergers with mass on the y-axis, what was on the x-axis?
Oh,
Asks Laurel.
there was nothing on the x-axis. It was just to spread them out. Yeah, they weren't in any sort of order in time or anything.
Okay. So Alexa is asking, is an event horizon a conjecture? Are conjectures made by humans?
So the event horizon is not a conjecture. The conjecture, Penrose, the cosmic censorship conjecture, was that all singularities formed by gravitational collapse would be surrounded by an event horizon. Okay, so it might be possible to have gravitational collapse to form a singularity that isn't surrounded by an event horizon. That would be a bit of a disaster, because then there would be what are known as naked singularities, which are a breakdown of general relativity that, you know, might propagate out and do horrible things in the universe. But it's conjecture, and it's, you know, there's actually some reasonably good reasons to think that that all real collapses of matter will be surrounded by black holes. But there is no mathematical proof of that.
Okay. Let's see. How does stations like LIGO point us in the direction of where ripples originated from?
Okay, so that's interesting. Actually, the gravitational wave detectors like LIGO have relatively poor directional sensitivity. They're not like telescopes where you have an aperture and you point in a direction. You only get light coming from that way. They detect gravitational waves coming from all over the place. But the reason that we have so many of them scattered around the globe is so that when a gravitational wave passes across the Earth, it hits the different detectors at different times. And from the time that it hits the different detectors, we can figure out what direction the gravitational wave was moving, and so trace back towards the source. So that's basically how we were able to figure out to some relatively small region of the sky where the binary neutron star occurred.
Thelma is asking, is all the matter in the galaxy expected to eventually end in the galaxy's accretion disk?
No. No, not very much of the matter of the galaxy will be there, but occasionally one of those stars that we saw moving around in that star cluster in the center of the galaxy, eventually sometimes those stars get too close and get ripped apart and contribute more matter to the accretion disks around those things. But, you know, out where we are, we're perfectly safe.
Good. Do you think that wormholes exist?
Wormholes actually require rather exotic types of matter. So it's hard to imagine. We need a certain kind of matter that doesn't sort of matter with negative energy in order to construct a wormhole. We don't know that we can get matter of that kind at all in our universe, so they're looking kind of unlikely. Nevertheless, that didn't stop them from putting wormholes in the movie Interstellar. So again, hopeful, sort of hopeful reality.
Okay. Is the Einstein telescope under construction now, or is it still in the planning stages?
That is still in the planning stages. And I should have mentioned that there is also a concept for a larger version of LIGO called Cosmic Explorer. I didn't put it in because I like the picture of Einstein telescope better.
Okay, that's fair. All right, so do other things ripple space-time other than gravity? For example, do magnetic fields do anything like that?
Well, the things that ripple space-time have to do so through gravity, in a sense that it has to involve moving masses. So a magnetic field wouldn't really produce a ripple in space-time, except for the fact that electromagnetism actually does have, well, maybe not mass as you would call it, but it has energy, and the energy can function the same as mass. So in principle, yeah, the electromagnetic waves could in principle produce gravitational waves, but you would need, they don't normally have enough mass to produce waves of any consequence.
Okay. We have a child, Stephen, who's asking, can black holes ignite, combine with each other? Which you've talked to this a little bit, but maybe you want to reiterate.
Yes, well, so two black holes, in some ways of thinking, can come together and form one common black hole. Nothing comes out of this, though, apart from gravitational waves. Again, these are complete vacuum things. There's nothing there. So there's no burst of light or anything like that. So there's nothing igniting in that sense. But they do produce a large amount of these gravitational waves when they merge.
Okay. Do black holes radiate heat?
Do black holes radiate heat? Not classically. So black holes are these one-way membranes that don't radiate anything. Although it turns out that Hawking showed that when you look at a semi-classical, or partly classical, partly quantum view of black holes, then black holes can actually do radiate, produce radiation. And the temperature of the radiation scales as the black hole mass, but in the sense that bigger black holes produce much colder radiation. So the black holes that exist in our universe, or the ones that we know about, don't produce any radiation, or so very little as not to be noticeable. In fact, they're pulling in more radiation than they're producing. But if we had a black hole that was very, very tiny, say so tiny that, say, it's a mass of a cell or something like that, then it would be extremely hot, and a black hole that size would almost instantly evaporate, radiate away all of its mass and energy.
Wow. We have some thank yous, of course. What causes gravity? Richard knows the equations about gravitons and the effects of gravity, but what's the cause of gravity?
So in Einstein's relativity, the cause of gravity, gravity is described in terms of the space-time, the geometry of space-time. So it literally is the geometry, but when you put in time, you can create curved geometry that has that basically produces the effects of gravity. So things falling around other objects are basically things moving in straight lines, but in a curved space-time. And so the gravitational motion that we see is due to that curvature of space-time. And the tidal effects, the things that pull you apart as you fall into a black hole, are created by strong curvature of space-time curvature.
Scott says, a wonderful talk, Dr. Creighton. Is it possible for some of the biggest supermassive black holes at the center of galaxies to ultimately swallow these galaxies themselves, or is it their gravitational pull not that strong?
It's not that. I mean, they are massive objects in the center of galaxies, and they dominate the motion of the stars in the very center of the galaxy. So the star cluster that we saw earlier, all those stars are clearly moving under the influence of that massive black hole in the center of the galaxy. But those black holes, although they're massive, millions of times the mass of the sun, they're the mass of the galaxy, and even the central bulge of the galaxy, is much, much, much more massive than that black hole. So the motions of all the stars in the galaxies is mostly not affected by the black hole. It's only the very inner part of the galaxy that's affected by the black hole. So it's quite unlikely that those black holes are going to grow to be big enough that they will consume a galaxy.
Can you comment on the two neutron stars merging to make a black hole that was on your plot?
Yes, so those two neutron stars that merged, although a huge amount of matter was released from those two neutron stars out in that explosion, most of the mass of those neutron stars got packed together and was ultimately too massive to be a stable body anymore, and so would have undergone the complete gravitational collapse, just like in a more massive star. So the end point of that merger was a black hole, but in the process, a lot of the material of the some fraction of the material of the neutron star was blown off. So even that big billowing cloud only had a few percent of the total mass of the two neutron stars. Most of the mass of the neutron stars ended up in a black hole.
Okay. People are appreciating your good effort to make this approachable, even though it's a technical talk, of course. Let's see. We have, what about a white hole theory?
All right. So
asks Hannah.
So in the exact solution, the Schwarzschild solution, you might have noticed, I don't know, the solution is not just a black hole, but a white hole. So a white hole is like a time-reversed black hole. It's got a horizon where if you're in the inside, you've got to go out, and nobody on the outside can ever go in. And that it has a naked singularity. So it has a singularity that is visible to the outside world because it's inside the white hole where things always get out. People have speculated that maybe something like a white hole could be related to something like the Big Bang. The Big Bang, by the way, is an example of a naked singularity. So it's not like naked singularities don't exist in our universe. There's at least one that exists, but it wasn't formed by gravitational collapse. But the white hole singularity turns out to be quite kind of different from the Big Bang singularity, and in some mathematical ways. So we don't think that the Big Bang was actually a white hole singularity. But again, this is an exact solution of Einstein's equations. It, in principle, could exist. In real black holes, the white hole portion of that space-time gets covered up by the star, so it doesn't actually exist. But maybe there could be white holes out there. If there were, then they would be violating the cosmic censorship conjecture.
So great. So there was a question I wanted to, what are some of your favorite questions about the universe that you would like to have answers to in your lifetime?
Oh, that's a great question.
That's Joel, yeah.
That's because it has nothing to do with what I talked about today. One of the mysteries that I described is where did these supermassive black holes come from, and I think that's something that I'm particularly interested in. But there are other mysterious things about the universe that I think are going to be perhaps more perplexing, and those have to do with the dark matter that Jean was talking about before, and also something else called dark energy, which is causing the universe expansion to accelerate. And of course, another big question that I'm very interested in is to understand where general relativity is breaking down at these singularities, and how theories like quantum gravity can reconcile general relativity's description of things at large scales with quantum mechanics describing things at small scales.
I'm not actually sure how to pronounce this word, but so Greg says, please explain Susskind's conservation of energy at event horizon.
Okay, I don't really understand a lot of the string theory approaches to event horizons. They try and they try and envision the event horizon not in the way that it is in general relativity, where it's just a it's actually not even really noticeable. I mean, in general relativity, an event horizon could pass through me at any moment, and I might not even notice. If the black hole was huge enough, it might just pass through me, and I wouldn't even notice that the event horizon has gone through me. It could be that the event horizon is dressed somehow with quantum phenomena, but I think that's very unlikely to be the case. The event horizons are very peculiar things. You don't ever really know where the event horizon is until you've lived to the very, very end of time. Because the only way you can know what wasn't in your past ever is by going on forever. So I suspect that a lot of the string theory notions of these dressing of horizons actually refers not to something called an event horizon, but to something called an apparent horizon, which actually lives inside of the black hole. So I suspect that even if these quantum phenomena at the surface of horizons happen, that it's already inside the event horizon, so it's already outside of our universe. So it's there might be some sort of string theory effect going on, but I suspect that's already past the event horizon.
Okay. Um, let's see. So we certainly have been, I'm wondering, yeah, Marina says, thank you. Even this non-scientist understood and enjoyed the talk. So that's great. I think we might take one more question. This is Emma's question. Is the singularity creating all of the effects from a black hole?
Well, that's interesting because you can sort of say yes or no to that one. The singularity is where all of the mass of the black hole is. And in some sense, the black hole is nothing other than its mass. But that's also kind of not the right answer, because singularity is inside the black hole and it's not even in the portion of the universe that can influence our universe. And of course, we do feel the gravity outside of the black hole. So it's a little bit of a complex concept. The singularity is not actually causing anything outside, but it is where the mass that is causing the stuff outside is located.
Okay. I think, given that we certainly have gone a little over time, but you had excellent questions and you gave an excellent talk. Thank you so much for packaging a complex topic in a way that we can follow. I'd like to thank everyone for attending. I would also like to point out that the planetarium does have other virtual programs this summer, and if we could put please in the box where people can see the planetarium website, that you can see the programs. We'll have also programs for members only in June and July. And of course, we'll have a Dodging Doom program in July, and also a celebration of shooting stars in August. So I know that you are eager to thank the speaker. So thank you again. And thank you, Victoria, for running the scenes behind. Without Victoria Robinson, this is a very tricky exercise indeed. And thank you again for joining us tonight.